All right. Good morning. Let's recall quickly what we talked about last time. The story was about how we develop understanding of interactions on graphene, an analogy with quantum electrodynamics, and as we discussed, there are indeed some analogies. I'll just show, for a reminder, notes that I typed. So what we started discussing is the graphene as an analog of QED. People call it poetically QED in a pencil trace. Then, so we'll finish that today, and then also talk about the effects which are important for the story from last week, the effect of interactions on the gap, and then next time we'll talk about spontaneous ordering, excitonic superconducting, etc., and if time permits, collective modes, new collective modes. Right. So all right, so this is a quick reminder. When we say that graphene is a model for QED, we should be careful in that there is analogy on the level of the Hamiltonian and interactions and symmetry and topology, and theoretical framework. From experimental point of view, of course, it's very different because in high energy physics you do scattering experiments mostly and use energy as a knob, and in condensed matter we have Fermi C, so all states are filled up to a certain level, and we typically perform transport experiments at the energy near Fermi level. So the Fermi level, which can be tuned by gates, serves as a knob equivalent to energy in high energy physics. But up to that, there are indeed analogies. And then if we go on to describe many body problem, this is what we get. 4 species of single particle Fermi relativistic Dirac systems associated with 2 values and 2 spin components, and then interactions, and we discussed the corrections to that, but we're not going to worry about corrections today. So we're going to assume that we are in the limit when characteristic particle wavelength is much larger than lattice constant, and then in this case we can model interaction pretty accurately by one of our Coulomb interaction, but if needed, corrections can be added. Then the fine structure constant, if we estimate it as the ratio of potential energy to kinetic energy, is scale invariant, and that's a consequence of the scaling symmetry that we discussed last time. And the value is 300 times larger than the QED fine structure constant, and so it's a order 1. And so the interaction strength, if you compute it, including all relevant dimensionless factors, is also order 1. So interaction effects are important, so we have to understand them. And the simplest way to model it, and also to exhibit the analogy with QED, is to write down, use relativistic notation or quasi-relativistic notation. Speed of light sent to infinity. Instead of speed of light, I have Dirac Fermi velocity, and I can write effects of action as we did last time in this form. Free particles coupled to that live in 2 dimensions, and they're coupled to electrostatic field 3 dimensions, and that's the interaction vortex. And discussed Feynman rules for this QED fermion propagator and field propagator, basically given by 2-dimensional Fourier transform of one of our interaction. And so if we if we try to compare it with QED, we see that there are two main differences. First of all, it's two-dimensional versus real QED being three-dimensional. Second, the photon is instantaneous. But it turns out that these two things somehow compensate each other, and the power counting for Feynman diagrams is basically the same as in real QED. And so we get log divergences, and we can develop perturbation theory to treat these log divergences. When we handle log divergences, we have to introduce cutoff, and the UV cutoff is usually at the lattice scale and is fixed. And that's different from real QED, where UV cutoff is a running cutoff, and we're interested in how low energy properties such as electron mass, charge, etc., G factor, scattering amplitudes are renormalized as a function of UV cutoff. Right. So there are two main ways to develop perturbation theory to handle log divergences. And so one is assume weak coupling, even though coupling isn't weak. And that's conceptually closest to QED, and we'll start with that. The other approach is to take large n limit, and that will be suitable even for coupling constant of order 1. But anyway, however you proceed, have to continue later to realistic coupling constant and values. And so let's start. We can take basic Feynman diagrams, polarization operator, self-energy, and vortex correction. Sorry, I forgot to put it here. And evaluate them. And so we'll start with weak coupling and then discuss the large n case. Okay, so so I can write polarization operator, and in this quasi-relativistic notation it will look like this. Right, and this bar means that you have an inner product with Dirac gamma matrices. So various factors of I that were in the interaction vortex and also in the Green's function, they all canceled, right? So right. So we can evaluate this quantity fairly easily, first using Dirac algebra and writing these Green's functions like this, and then also using the trace for gamma matrices. That's right. So you can either derive this or look it up, and whichever you prefer. mu rho delta mu sigma plus delta mu sigma. Delta nu rho. So if you use these, if you first use this, then use that, then you can write down polarization operator as for n because of this factor and then there will be an expression that will look like yeah, I think that's right. Okay, so so now we have to evaluate this integral, and in QED we learned how to do it. We can use Feynman parameterization. Should we switch it off? Yes, there was a question? Yeah.
What's the definition of gamma matrices? Should it be like eta in the last case? Should it be the Minkowski matrix?
Right, so we are, okay, sorry, I forgot, I should have pointed out when we were looking at the notes. We're doing it in Euclidean space because we did weak rotation. So our effective action is in Euclidean space, and in particular gamma matrices, anti-commutation relation is Euclidean metric. Okay, I mean you can always rotate back and add an I factor, and then you'll be okay. So we can compute this using Feynman parameterization and writing, writing 1 over, two things as the integral over auxiliary variable. Of this thing squared, and then after you do that, you get an additional integral, but then you get a simple expression on the denominator, and you can shift variables and perform other things. So this is rather standard. I'm not sure if I need to get into show you the details of how this is calculated. Maybe one comment is as follows. If we do power counting, then we should get worried even before we started computing this integral because this is momentum to the power -2, and this is momentum to the power 3. So this integral nominally is divergent. However, I know that because of particle conservation, there is a constraint on polarization operator, that polarization operator will be 0 whenever space-like component vanishes. The reason is that polarization operator for spatial uniform, for 0 incoming spatial momentum describes density response to uniform oscillation of the background, and of course there is no response density to uniform oscillation of the background, so charges don't move in response to that. So pi will vanish, and it's an argument very similar to what is used in QED in a similar calculation, where they encounter similar problems, so they use similar type of argument. So the moral is that we shouldn't be worried about this potential divergence. We should just think carefully about what happens at q equals 0 at q equals 0 and q non equals 0, and then we'll be all right. So with that comment and with Feynman parameterization, this can be easily calculated, giving unless you want to, I can show some details, but basically.
I just have I think this would be obvious in the Minkowski space, because somehow you're not applying any force to the system. So,
that's right.
But in the Euclidean space, somehow it's like as if you had introduced canonical ensemble, and somehow don't you shift the chemical potential, and then could it change the particle density? But you're saying the particles, they are not allowed to come from, there's no external reservoir for this system.
That's right. So
it's canonical ensemble, but not grand canonical
ensemble. Yeah. That's a good point. We are using this intuition based on Minkowski space that particles can come and can go. Right, in the Euclidean space, all coordinates are equivalent, so it's not so obvious, but in Minkowski space, this is true. Yeah. So anyway, so if you use this and that, you arrive at the answer, which is very simple. And looks like this. And after weak rotation, it becomes it looks like Q omega, so it will be K squared over V squared, K squared. So here I mean, when I was doing calculation, as people always do, I set early on, I set H bar and V equal 1, and then at the end I restored correct dimension by putting it H bar and V. So that's what that's what you get. So what you looking at this expression, you see that you have a particle hole continuum for omega greater than Vk, and that comes from analyzing the imaginary part of polarization operator, which is non-zero when omega and k is such that you can excite particle Hall excitation. And so only when omega is greater than Vk, we have particle Hall excitations. That has a simple explanation, because we have this band of states with all these states being filled, these being empty, and so in order to create particle Hall excitations, we have to make an interband transition and create a hole here and a particle here, and you can see very easily that any frequency and momentum difference required for that satisfy this condition. Also, we have a singularity at Dirac cone. Square root singularity at Dirac cone, and that comes out and to be important in various effects. And also, just for those who are used to thinking about Fermi liquid, for comparison, let me write down an expression. Conventional expression for polarization operator for Fermi liquid, which is Fermi C, some dispersion relation, quadratic or linear, whatever, with the Fermi C, and then phi k omega is so let's say if I put Fermi level here, make it doped. Great, then I will have this expression, which is true for omega, which is true in the opposite limit to that. It's true when omega and Vk are much smaller than the Fermi energy. So if you are considering particle Hall excitations in the vicinity of the Fermi level, if you have a Fermi level and you have particle Hall excitations in the vicinity of Fermi level, which is what we always do in Fermi liquid, then that's the expression. And so it's so in this case, particle Hall continuum will occupy this region, right, as opposed to that, because for excitations near Fermi surface, as a relation to produce particle Hall pair, for relation frequency and momentum to produce particle Hall pair is the opposite to what we have. Just for, we're not going to use it. This is just for those who know too much. Yeah.
What's the n in front of the integer?
Oh, n. Sorry. So n is my number of species. So that's valley plus.
Is there a difference in the way you treat up and down spin, or can say prime, like in this scattering? Like you just have 4 copies of the same expression?
Yeah, so I have 4 copies of Dirac, massless Dirac fermions, and there are small differences in the Hamiltonians, single particle Hamiltonians, points k and k prime that we discussed last time, but you can absorb these differences in redefining pseudo spin components. So you can write it as 4 identical Hamilton, hiding these differences and redefining pseudo spin. You can write it as a 4 identical copies of Dirac fermions interacting with each other.
And the spin, same thing. The spin, you said valley you can hide.
Right, but spin up and spin down are totally equivalent unless you apply magnetic field. But we're not going to apply magnetic field today. All right, so that's polarization operator. The most important thing is that we don't encounter any log divergence. So So the same, the same way as in QED, there is no log divergence. Yes.
And so by the particle number conservation, did you subtract some infinity from this integral?
That's right. So if I I can subtract some infinities, or I can say that all this came from some block band where there'd been no infinities in the first place because all the integrals were finite and they were cut off at lattice scale. So, and in the block band, this still holds. There's no particles can't appear from nowhere. So I know that I had this even before I made an approximation that led to my relativistic description. So it should be maintained throughout. Okay, so no log divergence. That means that I have to go to my second diagram and then to the third diagram until I find log divergences, right? So the self-energy diagram self-energy diagram. So I can write an expression for self-energy, again using pseudo relativistic notation. And I did this transformation on the Green's function that we discussed over here. Actually, I forgot an I in it. So an I here. Right. So I did this, and then there is also the propagate of my photon, which is taken at momentum q, and so this thing is simply G over 2Q space-like, and G is my coupling constant that we defined like 4 pi square over kappa, the dielectric constant last time. Okay, so this diagram is going to be log divergent. However, let's before we get there, let's just stare. Before we calculate, let's stare at it and think a bit at what we see here. So first of all, it's not Lorentz. This expression is not Lorentz invariant, even though Dirac fermions are. But because there is this coupling to non-Lorentz invariant propagator, self-energy is not Lorentz invariant. Because it's not Lorentz invariant, we can expect that there'll be a renormalization, for example, of Dirac Fermi velocity, as opposed to QED. In QED, speed of light cannot renormalize because everything is Lorentz invariant. So you can't. If your calculation is correct, you can't generate renormalization of the speed of light. And here you can. Right. So that's point number one. Point number two is that here there will be a log divergence, so I'll have to handle this logarithm by integrating over momentum shell. And then when I do so, what I expect to see is that sigma sigma of p will have some general form that I can write down as, sorry, write down as follows. In a theory where I had Lorentz invariance, sigma 1 and sigma 0 would be equal, but here they're not. So if they were equal, then I would generate a term that would look identical to what I have in the Green's function over here, and so there will be no change of the speed of light. But because sigma 1 and sigma 0 are generally different, then you generate velocity normalization. Okay, so how does that happen? Let me move on. Right. So what I have to do to see velocity renormalization, I should take a renormalized Green's function. G, which is obtained from making all self-energy insertions and summing. Summing all of that, starting, of course, with a term with no insertions, then that will be given. I mean, these are geometric series which I can resum and write the answer as follows. Sorry, right? So now looking at this, and we haven't yet computed sigma naught and sigma 1, but we will shortly. So looking at this, we can observe the following, that the velocity will be determined by the ratio of the space-like part and the time-like part. So the velocity will depend on the ratio of this factor to that factor. And then, so it's convenient to factor out this and absorb it into a normalization of Z, the residue. Residue, or in QED, it's called wave function amplitude. Renormalization via Z minus 1 equal to 1 minus sigma naught. So we may have that, and also we may have velocity renormalization. So my new velocity, and here there was a bare velocity, So my new velocity will be related to bare velocity by this formula, which, I mean, since I'm going to do perturbation theory, both this and that is going to be small in perturbation parameters, so it's more natural to write this as delta V equal to Taylor expand and write it like this. So that's the simplest way to analyze velocity. Right. So with that, we're ready, to compute the integral. And indeed, if you so you take this, and then you note that the frequency only appears in the Green's function, but not in the propagator, because it depends only on momentum, on the space-like part. So because it appears only here, and because this is a rational expression, you can integrate over frequency, and basically it's a Lorentzian, integrating Lorentzian, and throwing away terms which are odd in frequency in the numerator. And so that's the first step. That is easy to do. So integrate over Q node, and that gives sigma of P, which is minus G over 2. Let me write down and then explain. And then there's that, and then there's P minus Q modulus. Yeah. Okay, so this is what have become of my Green's function after integrated over Q node. This is the propagator, and after you integrate Lorentzian, you get a factor of pi, and then this was 2 pi cubed, so there is an additional factor. Can move it out and absorb in the prefactor, and G over 2 is the propagator. Okay, so next, what we can do is say that looking at this and doing power counting, you see that if you extract terms which are proportional to P or to P node, then the remainder will be dimensionless, and so you expect the remainder will have scaling dimension 0. And so that means that you will get a log. And so indeed, if you take that and linearize with respect to P node and with respect to P, you get sigma node and sigma 1. You can see already before you started doing it that the sigma node is going to be 0 because P node doesn't appear anywhere. So if there's nothing to linearize, right? But sigma 1 will be non-zero, and that if you linearize this with respect to P, saying that P, the external momentum, is small compared to the inner momentum flowing in that loop, then what you get is linear in P multiplied by log divergent integral over Q, and the result. You can basically read off the result from what you see, and it will look as follows. So G over 4 instead of G over 2 because there is 1/2 coming from here, and then there is integral over Q should be evaluated in my energy shell, and then there is an additional factor. So this is from linearization, and then if there is an additional factor 1/2 that comes from integrating of angles. You might think naively that you only need to extract P from here, but that would give a result which is twice bigger than what you actually get if you linearize both respect to this P and this P. And then, so that 1/2 comes from integration of angles. Okay, so we finally arrived at the log divergence. Yes.
Where do you get the vector gamma? Because there's no vector gamma.
Oh, gamma. Sorry, gamma was sloppy. So this was actually P. I mean, this was part of the Green's function. So this was this was P spatial. Okay, let me write it. P spatial, Q spatial in a product with gamma spatial, and then gamma node. So this came about when I took this expression, and then here I have P node, gamma node, and also P1, P2, gamma 1, gamma 2, etc. And I integrate it over P node, and I'm only left with spatial parts. That's the thing. Sorry. Okay. Yeah. So that's that. So what we find is sigma 1, which is, if you put together all the factors, you get log times this number, and then sigma 0 is 0. Okay. Right. So lastly, we need to compute vortex correction. Yep.
Can you repeat again how do you get dq over q? Because just looking at the integral, you go, let's say, to polar coordinates, q over q cancels. And it doesn't look like you have divergence at 0.
I take P small, so you have also P minus Q. And because I think you take...
That's right. So let's say, I mean, naively what I can do is say that let's set Q equals 0. Let's say set P equals 0. Set P equals 0, I get Q vector divided by Q square, and that integral should vanish by symmetry. Right? So, I mean, nominally it's divergent, but we don't care because by symmetry it's 0. So next terms that you get is by linearizing with respect to P. Let's say take this P vector in a product with gamma vector, and then ignore P elsewhere. Then I get P gamma factored out, and then here I get D2Q over Q square, and that's a log. Right? And then what I was trying to say, but it was too fast, is that this is not the only term in linearization. There's also a term in linearization coming from here. So you can forget about this P, but extract term linear in P from here, and it's going to give some angular integral, but after you compute it, all it does is reduces the factor of 2.
Is there some initial ways of thinking about infrared cutoff? The UV cutoff is just laser size with block infrared cutoff.
Yeah, so infrared cutoff in condensed matter is flowing. So we don't know, what length scale.
System size maybe could be.
Huh?
System size after all our sample.
Well, yeah, system size. But before we arrive at system size, there is, if we discover that our observables change in some way, then there'll be maybe correlation length or phase transition or some characteristic length at which we enter weak coupling or strong coupling. So in condensed matter, we have to study what happens as a function of infrared cutoff. So that we fix the higher cutoff at lattice scale, and then the lower cutoff will be flowing. But that's the idea. But then the way we implement it is that we don't integrate from lattice scale all the way down to to our actual correlation length, but we eliminate, because we're getting log divergences, we eliminate shells one by one. And so we have to look at all the quantities where log divergences occur, and then study how these quantities change when we integrate out variables in different shells and how they flow. In this case, it will be particularly simple because only one quantity will change, as you will see, right? So polarization operator is not generating any log divergence, and then the vortex correction also not doing anything. So if you take this diagram and then write it out, then there is a Green's function, another Green's function, and propagator, and that has scaling dimension minus 1, minus 1, minus 1, and you integrate over D3Q, so potentially this is log divergent. However, if you stare at this expression, you will see that in the same way as that, if you take incoming spatial momentum equals 0, you can show that this vortex correction is identically 0, and you can probably relate it to the same particle conservation. There's also another interpretation that we're going to discuss shortly, but in any case, this is non-divergent. So sorry, when I say it's 0, I only mean the log divergent parts. There's also non-divergent parts, but they're small and they're not of interest at leading log order. So basically, what you end up with is that you can combine all of these findings together as follows. You can say that you have the only quantity that renormalizes is velocity, so your renormalization group flow for velocity is for velocity only, and what we found is that you get for h bar. I'm restoring all the dimensions, all the numerical factors, and setting dielectric constant to 0. So this divergence that we found here. Okay, sorry. So I should put in coupling constant, which is 4 pi e square, and after that 16 pi will generate factor of 4, and e square over h bar is what I get. So right. So that's the change in velocity, and
times the bare velocity.
Times the what?
The bare velocity.
No. So yeah. So when you restore, this is very interesting. When you restore correct dimensionality, the bare velocity drops out. Dimensionally, e square over h bar is velocity. I mean, there are two ways to see it. First of all, our fine structure constant e square over h v is dimensionless. Second of all, e square over h bar is velocity of electron on a Bohr's velocity of an electron on Bohr's atom. So e square over h bar is in fact velocity. And it's awarded 10 to the 6 meters per second, comparable to velocity in graphene. So there's no bare velocity here, and therefore what happens when you eliminate variables in different shells is that you get changes to velocity which are added up, and so velocity grows linearly, if you like, as a function of RG time. Most important thing that we found that I forgot to articulate is that velocity grows because there is a negative sign here, and that means that correction to velocity is positive, and this is 0. So velocity grows. At low energies. Right? And that means that instead of Dirac cone, I get Dirac cusp. Right, for the dispersion relation. Okay. Also, E square electron charge is not renormalized. Not renormalized. So this follows from basically having no vortex correction, but I mean it's a bit more general because you might think that the fact that electron charge didn't renormalize was an accident, that we got some cancellation in the integral. So when people saw that, they went to next loop order and started looking at the next loop order, and so at the next loop you find various other corrections that may be log divergent, but the effective value of electron charge is still not renormalized. The general reason for that is that electron charge, if you remember our effective action, it appears as a coupling constant in front of a singular term. There is this Coulomb interaction which is long range. And if you write it in momentum space, then you get a term which is singular in P. And so the singular term doesn't acquire any corrections. If you consider perturbation corrections to particle-particle vortex, then there are no, of course there are corrections, but there are no corrections that generate vortex which is as singular as Bayer-Coulomb interaction. Because of that, Bayer-Coulomb interaction doesn't have its strength does not have any renormalization, and you can people actually look carefully into it, and indeed you can show that. For example, if you take this at high order, take some high order correction, let's say two-loop correction like this, then this diagram may generate a non-zero and log divergent delta gamma, but in order to renormalize effective charge, you need to multiply gamma and z, the amplitude of the wave function. So the same way, the same correction as you get for gamma at second loop, you also get to z, the quantity which was 0 at first loop, and then their product does not renormalize. Right. So, but you don't have to. I don't want to get into two-loop calculation for sure. Too long for a blackboard. But there is this general reason why E square is not renormalized. That easy to understand. And so let's go with it. Okay. Yep.
But alpha does flow, right?
Alpha does flow. Yeah, that's my next point. Absolutely, alpha does flow. That's very important. So alpha flows in exactly the same way as in QED. So alpha does flow. And so this doesn't flow, but this does. And so combining what I found here, I can write change in alpha as minus alpha square over 4 log lambda node over lambda 1. And so that, to handle that, it's convenient to rewrite this to write this difference equation saying how much alpha changes when I change length scale from this to this. I can write this as a differential equation. I can write it as how alpha evolves if my RG time, which is log of momentum, increases, or momentum goes to lower values. And so, oops, no minus sign. Yeah, so change in alpha is negative when I add, when I go to larger and larger length scales, and so when P flows from large values to small, alpha will diminish, and so alpha will flow to small values, and at small, asymptotically, if you solve this differential equation at small values, you will see something like 4 over log of lambda over P, something like that at large distances. So it flows to weak coupling. As in real QED. However, for a different reason. Real QED, speed of light is not renormalized, but charge is renormalized, and here it's the other way. Right? So, but formally, it looks very similar. All right, so, oh my God. All right, so, yeah, I think I showed all yeah, so this is a weak, I mean, sorry for this being a bit slow, but I wanted to do something on the blackboard that we see where log divergences come from. And so this gives an idea how these calculations are done. So now I can jump to large N, and then rather than doing this all over again, just comment on the differences, right? Yeah.
So we have a simple heuristic explanation for why the velocity is increasing, not decreasing.
Yeah, I think it's because basically this is a Hartree-Fock correction that does it. You get two bands, and the states and the self energy. If you take your outer state, let's say, in the conduction band, and then integrate all the states, then the main contribution will be states from the field states from the real band, and then the states will repel each other, so to speak. So they'll suppress the density of states and make dispersion steeper. That's general. I mean, if you look at the ordinary Fermi liquid, what's the Hartree-Fock correction? Fermi liquid correction to velocity, it will be the same story. It will be positive for the same reason, because it arises mostly because of virtual particle Hall excitations across the Fermi level. The same thing here. We get a reduction of density of states there because of that. Yeah. Yes.
So this sort of, you have classified this question that was somehow observed experimentally.
Yeah, I'll show data. Yeah, of course. Right. But before I show data, I want to talk about large N. Yes.
Is there a way to somehow make the whole thing self-consistent? Because in some sense, this suggests that one should start with the propagators in which the dispersion has this cusp, and somehow compute the diagrams with,
well, I mean, this is only perturbation theory, so I'm not claiming anything yet about the real thing. But I mean, we should do perturbation theory and then see if results continue nicely to. So I mean, I'm not trying to make it self-consistent. Just weak coupling is, and so maybe actually this is a good.
Just come back to your answer. So in the Fermi liquid, I'm confused now. So VF star, so the Fermi velocity, which is normalized.
Yeah.
The VKF over M star.
Right.
And the mass grows in interactions. So you're saying that the velocity decreases in Fermi liquid as well?
So
it's decreasing because you're dressing the electrons, so it's heavier.
Yeah. So the Fermi liquid. So there are two contributions to Fermi liquid renormalization: Hartree and Fock. And Hartree usually is larger, except special cases. In the limit of strong interactions, people think that exchange correction, Fock correction, dominates, and then what you said might be true. But if you start with weak coupling, then Hartree wins, and then velocity increases, the density of states goes smaller.
So what is the threshold?
Let's not talk about Fermi liquid. I mean, we'll discuss it later. I mean, I have enough. I'll be happy to. I'll be happy to discuss it, but I think it will not help anything here. Yeah, so there is a threshold, of course. If you start at weak coupling, then you see one sign, and then when you go to stronger coupling, you see the other sign. It's complicated, but I'm not sure if we. Yeah, I want to finish this. I only got 24 minutes. So let's. Can we postpone? All right. Okay. Right. So. So yes. So what? What we can do is start with your question and say that if we really want to go to strong coupling, then we should either take weak coupling and then sum over many orders of perturbation theory and try to make sense out of it. But then there are lots of diagrams, and actually people looked into it and didn't get very far. There is another approach which seems to work better, which is to say, let's forget about weak coupling approximation, allow coupling to be order 1, but take n to be large. Take my number of species to be a knob, and take large n limit, and then if you take n to be large, you're allowed, you are okay with coupling of order 1. And then this approach seems to work better, and I erased this. I was hoping I can use the board. Right. So you can basically go through the same steps, but with interaction modified in large n limit. So and modifications are minor. So let me just talk about that. And access strong coupling, then use large n to control perturbation theory. Then what happens in a large n limit is that your perturbation theory is dominated by contributions with maximum number of fermion loops, because each fermion loop contributes a factor of n summing over number of species, and so you get leading order contribution at large n when you try to maximize number of loops at every order of perturbation theory. And what that what that amounts to is that you use well, first compute the simplest one-loop diagram, which is polarization operator, and we already done that, and this was the reason we computed it, despite that it wasn't log divergent. Right? So it's proportional to n. And then other diagrams that we computed, sigma and gamma, they didn't have any fermion loops, so they were order 1 at weak coupling. Forget about logs for a second. So looking at this means that we need to maximize number of polarization operator type diagrams, and we can do that by taking interaction and putting polarization bubbles in it. And so I resum it in the same way as series for the Green's function. And so in a large n limit, I can approximate it by taking a leading term, which means that here n, the term proportional to n, will dominate over this factor 1, and if I forget about this factor 1, I get an effective interaction that looks like 1 over pi of q. Pi is proportional to n, and so my effective interaction is 1 over n. So that means that in the limit of large n, I get effective interaction which is weak, and so I have a well-defined perturbation theory in 1 over n. Also notice that dependence on coupling constant that came in through here disappeared. So instead of my original coupling constant, which was 2 pi squared, blah, 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 my new coupling constant in large n limit is 1 over n, more precisely 16 over n, something like that. So in large n, this is my perturbation parameter, and so what I can now do is say that I will take this effective interaction and then with it compute all quantities of interest, self energies, and vortex correction, and then see what happens. So if you do calculation for self energy, what you find is that both sigma node and sigma 1 are non-zero, meaning, both log divergent. And that gives, again, a renormalization of velocity, which is obtained from this difference times my real velocity, and it's of the form it's of this form, and now this is multiplied by the Bayer velocity. I mean, electron charge is gone completely in a large n limit, so V is the only quantity dimensional velocity that is left. And then also there is a renormalization of Z, which appears, and let me write it down just for information. So it's a bare Z, which originally was 1, but it may change in the course of RG flow times RG log times this prefactor. Then you also get a change in the vortex. You get the vortex correction, which is always such that change in the vortex correction plus change in Z cancel. And you can trace it to word identity, or you can trace it to this argument about charge not renormalized because it's a coefficient in front of a singular term in the action. But you have both renormalizations, but they satisfy this constraint. So anyway, so we from that we can read off the RG for velocity. You can write equation for velocity renormalization. So this is different. This is different from what we have here. So this, if I write this what I get for weak coupling in the same form, I would get just E squared over 4 minus sign H bar. And so V will grow linearly as a function of RG time. And this gives V that grows exponentially as a function of RG time, or as a power law as a function of momentum. So it has a solution which is V of P, which is the bare V times lambda over P, lattice cutoff divided by P to the power beta. So it's and beta is this number. So we got beta, which was 8 pi square n. And so this is the outcome of this analysis. If you qualitatively, it looks similar to what you get here. You still get the cusps, except that this singularity is not just a log singularity, as in this case it's a power law singularity. So your dispersion relation is in a large n limit. The dispersion relation will be some prefactor times P to the power 1 minus beta. Okay. And beta, so this is the answer for beta at leading, at large n at leading order. You can improve this in various ways and go to loop, or go to make various other approximations. It doesn't change too much. So this is roughly what you get. And numerically, so 8 and pi square almost cancel, and 1 over n is 0.25. So beta is about 0.2. Not, it's a small value, but non-zero. And right, so let me just try to speed up a bit and switch to view graphs. There. Okay, so it's warming up. It will take some time. So maybe while it's warming up, I'll have time to say something else. If you try to summarize what we discussed in one RG flow diagram, and so we looked at what happens at weak coupling, also what happens to coupling at large n, and we found that coupling flows to 0, and then if n is large, you can continue this to arbitrarily weak coupling. So we covered we did calculation which covers this region, and then here you have what people believe a strong coupling region where the behavior is different, and so the phase diagram, we'll get to that next time. But what people think is happening is that in the region where we have graphene, normal graphene behavior and the semi-metal, our theory predicts that velocity grows and fine structure constant decreases, and coupling flows to 0. And then here we have an insulator where gap spontaneously opens up in the direct spectrum due to interactions, and it's an excitonic insulator of some kind. So it's a state with excitonic order. And then people worked on, trying to determine this threshold and this threshold, where is the boundary of excitonic state from this side and from that side, and we'll discuss that. Also, discuss other things. So let's see. So now I wanted to show experimental data. Right. So this is what we discussed. Oh, sorry. Right, so this is what we discussed, the large n approximation, and how dispersion changes. Then there was an attempt to measure it, not, probably not the last word, but this is the only direct attempt to measure it, so I have to show it to you. The group in Manchester tried to determine Fermi velocity as a function of doping. So you do transport measurement at a finite carrier density, and then study what happens if your carrier density goes to 0, and you find that Fermi velocity determined from the period of magnetic oscillations increases going to Dirac point, and so these are data points, and you can, and then the solid line is the prediction from weak coupling. So it's not this power law, but simple, 1 over log behavior predicted from weak coupling. And, the error bars are very high, so you can't really say much. I mean, definitely velocity is enhanced. If you ask whether it's enhanced stronger or weaker than predicted by coupling, I would say it's stronger, although these data points have large error bars and they're suspect. So I think it's qualitatively the effect is there, although quantitative discussion is still not done. Also, what you see is that overall velocity value is somewhat higher than velocity value at high doping. So there is some change from high doping, which means p over the lambda, to very small p. So velocity is enhanced, and this enhancement grows as we approach Dirac point, and qualitatively it's in agreement with this. But quantitatively, I think there are many questions. Okay? Yeah.
Temperature? Does it have anything?
So this was, I think they determined velocity from magnetic oscillations temperature dependence. They used this, you can determine effective mass from magnetic oscillations, how they change with temperature through, it's called Dingle temperature. And so they did study temperature dependence, and that's how this was obtained. But, I think there are many questions about how final this is. And you can see from scatter error bars. Yeah. Yes?
Is this pristine graphene or on some substrate?
This is, okay, most likely. So I think in this group they had better transport data for graphene boron nitride than suspended, although they did suspend it also. But I think in this case it was probably boron nitride. But have to check. Okay. Any other questions? So got 5 minutes. That's time gained. Let me talk very maybe briefly about another renormalization effect, which I think is of interest because of this gap opening that we discussed. One can ask the following question: suppose we have graphene placed on some substrate that introduces AB sublattice asymmetry, and let's ask, and it generates a bare gap in the Dirac Hamiltonian, and we can ask whether this gap is renormalized by interactions, and the answer is yes. And the diagram you have to consider is well, first of all, you have to add a perturbation in your Hamiltonian, which is of this form, and then you have to consider a vortex correction where this dashed line is this perturbation. So this is a vortex correction to Green's functions. There should be arrows here, and then this wavy line is the interaction, this propagator that we that we introduced. So the question is, compute this vortex correction and see what kind of RG flow it generates. Very simple exercise, very easy to do, and it proceeds basically in the same way as calculation of velocity renormalization. You have to take self-energy, and in the self-energy extract the term proportional to sigma 3, but also you have to worry about this sigma 0, because the renormalization of wave function amplitude, and the actual renormalization is the difference, in the same way as for velocity renormalization, it's the difference between sigma 1 and sigma 0. Here it will be the difference of sigma m, or defined in this way, and sigma 0. And so if you do large n, if you do it in a large n limit and calculate the integral, you get a log divergent answer, and the prefactor is is like this. So if you can compare it with our velocity scaling exponent and see that this is twice larger, then convert this into RG flow for the mass and see that you get power law with twice larger exponent than for velocity. So for velocity, the estimate was 0.2, so that would be 0.4, and 0.4 is already a respectable number, well, more respectable than 0.2. So this may be a strong effect, and indeed, effects of this type have been discussed before in various contexts. The first one, of course, is the QED radiative corrections to mass, which were described by Weisskopf, discussed by Weisskopf, even before QED was created. This log divergence has been known. Also, it's been discussed for those who are interested in topological insulators. This effect was discussed by Kane and Milley in their 2005 paper on spin Hall effect and graphene, where they opened up a gap in the Dirac spectrum using spin orbital interaction, but that was too small to generate a sizable gap. And they pointed out that this type of effect provides enhancement of the gap, and this enhancement. So I think the calculation that they did was in a weak coupling limits. So not large n, but small alpha. And when you do calculations small alpha, you generate an enhancement factor which is of this form. And again, comparing to what we did, it's a square of the enhancement factor for velocity. So velocity grows as this quantity in parentheses, and gap grows as a square of that in the weak coupling limit. And it's going to be, so of course it's going to be the same for graphene and boron nitride, or for any other problem where you open a gap in graphene spectrum. And if you take a bare gap to be what's estimated from realistic spin orbit interaction, which is a very small number, you can generate enhancement in a weak perturbation, in a weak coupling limit. You generate enhancement which is of order 15, and then this approach would generate enhancement which is a bit bigger. But no, I don't think we should talk about that. So what I'm interested in, but well, I'll show one more slide perhaps, is that this effect may be relevant for band gaps which are seen in graphene and HBN because there are some questions about how to explain the large size of the gaps that are being seen, and that maybe. So let me remind you a few things that we talked about when we talked about graphene and HBN. When you place graphene and HBN, then if you don't have axis alignment, you see a more rare type of structure where periodicity of the structure, of superlattice structure, depends on misalignment angle. And so that's the dependence of periodicity on misalignment angle, and also the periodicity mismatch between graphene and boron nitride. So you can control periodicity by angle alignment, and then so you see various new phenomena that we discussed, also ones that we didn't discuss. But Philip Kim will be here next week, and he'll surely talk about this and probably also about that. Right, and so my interest for me is this gap that opens up, which is seen from activation transport at the Dirac point, and then the gap can be measured as a function of alignment angle, and you see two things. First of all, you see that a gap is of few hundred Kelvin size, and also axis alignment is essential. So you can, for samples with different axes, you see gaps of different size, and I mean error bars, of course, are huge, and there are only four different samples. But you can still see a trend that when angle increases, the gap goes smaller, And the question is how to explain that, also how to explain the size. And the problem with the magnitude of the gap is as follows. I mean, we discussed it briefly, but if you try to analyze it, taking the coupling to substrate from ab initio calculations, then estimate the gap from single particle picture, then you get a gap only a third order of perturbation theory in the spatial in the Moiré modulation, and then you get a gap which is at 10 Kelvin at most. So this is at least 10 times smaller than experimental value, and so that factor of 10 missing in the single particle picture can be provided by enhancement due to interactions. So what you have to do is a little bit different from what we discussed today for gap, what we discussed before for gap that is opened by spatially uniform perturbation, because here you have spatially modulated perturbation, and so you have to do RG for the modulation amplitude, and then at third order calculate the gap due to that. And so there is some algebra that I don't want to go into, but if you do all the combinatorics, you find scaling exponent which is this number. It's 3 times beta times scaling exponent for the gap, minus 2 scaling exponent for velocity, and remember that this one was twice bigger than that one. So there is some combinatorial factor 4 that you gain in this way, in addition to what you already gained going from that value to value which is 2 times larger. So you get a fail because this gap arises at third order in perturbation theory. You get a small Bayer value, but also a large dependence on length scale, because it flows under RG with the exponent with beta value which is 4 times greater than the beta V value, right? So that's that's large enough, and it can generate enhancement, or the 10 enhancement that needs to be added to account for the observed data, for the observed values. So I think this is all, rapid enhancement. Good, right. So this is, I think I should stop here. Any questions? Yeah.
So in the large N calculation, the quasi-particle weight at the Fermi surface, at the Dirac one, vanishes, right?
Yeah.
Good. And
it does, right? So because we have, well, yeah. So you're saying perhaps I lost a minus sign here. Yeah, should be a minus sign, right? Yeah. So Z vanishes. Very good. Thanks. Yeah.
But the claim is that for pristine graphene, the weak coupling gives a better description than the more strong coupling large N approach. Because in the weak coupling, you don't predict the vanishing of Z and you get this enhanced velocity. This is the diagram pretty much.
Yeah. But Z by itself is not. The behavior of Z by itself is not necessarily of direct physical significance, because it only usually what you see is the combination of Z and vertex enhancement, and they are balanced by word.
But if you measure the spectral function of the
So if you can do measurement that will be sensitive to Z only, but most measurements are different.
But, so, overall, your claim is that the weak coupling approach is a better starting point the square?
Um,
Trying to.
So I think with treating interactions, 1 over n, people find to be more satisfying because it's easier to control. And it gives, if you go, so if you start with weak coupling and then go to higher orders and then try to sum up all these higher loop contributions, you don't get anywhere. And then for large n, the recent papers from University of Maryland that show that you get pretty good results going to 1 over n squared, and then it looks like it's all under control. I hear your question about Z and why experiments don't see rapid Z dependence predicted by this formula. We have to look at this experiment. Many of these experiments, including the one I was showing, and probably also the ones that looked at Z, they're kind of rushed. So they should be taken with a grain of salt, I think. Yeah.
So have people start studying this numerically, or is there some way to get some information here?
What about quantum mechanics?
So there are many people who claim that people who do lattice QED that claim that they can do this problem, and they worked on it. And I haven't seen anything definitive, but I'm sure that there are many people with lattice QCD background who have capability to do this calculation on carbon lattice, but somehow, and many claim that they're doing it or going to do it, but I can't report anything. I mean, people had more luck taking large n limit and then summing, evaluating numerically all or many of high order diagrams and adding them up, and it looks like you get good convergence. 1 over n squared, etc. Looks pretty good. But doing it on lattice, I'm not sure. I mean, maybe someone did it already. I'm just not aware of it. Okay, right. So next time.